Now in my lessons, this talk will be on basic vector operators, and this is again meant to be just an introduction to make my students in grade 12 aware of what these things are, and so when they see them again, they can have a little more insight. They know the basics of it, and they can start looking at the nuances of it. I hope that they'll, and so this won't be too long a lecture, but I make them simply be aware of these things and make them have them do some calculations. And I think it's just a matter of being a little bit aware does help everyone a little bit. So I introduce the vector operator del, and is represented by an upside down triangle, sometimes with the vector hat on it and sometimes not, depending on the mood. But nevertheless, we can do some things with del that tell us a little bit about what's going on. And this is overwhelmingly done in R3 only, okay? So del in its general form is equal to di x, comma, di y, comma, di z. Oops. Now, in its own right, it means nothing. Okay, it's a machine. Just like the pop machine, you put a tuning in the machine, you wait 3 seconds, and the machine has turned the tuning into a can of pop. It's a pretty amazing thing. And this is a machine, and when we add in some form or other a vector field, we will get, or a scalar for depending on circumstances, we will get these derivatives will act upon things, okay? So let's think about what we can do here. So how can this be combined with vector functions, and what might be the meaning, sort of the physical meaning, let's say, now I'm not going to always get into real life physical meanings. Sometimes we can, sometimes we can't. But let's have a look and see. So if we take a function, we could first take del, and we could use it with any function, and we could obtain, and we could create a vector value function. So let's suppose for a moment that we have, and I'm going to make a note of this course here already, so potential energy we'll use fancier symbols for things. So we used E sub p last year, okay? But now we're going to use V. You will find in most physics courses, by the time you get to the second year, we will use V for potentials. And you will be thinking volume or voltage, which we should never say is just a support. But nevertheless, it takes getting used to. And I find if we work on this a little bit ahead of time, it gets us past the nomenclature. And while I'm at it, kinetic energy was of course E sub k last year becomes T. You'll notice I didn't use P and K, okay? And some people do, or U is another favorite one. What I'm trying to do is to standardize things so that there's a limited amount of relearning things when you sit in a lecture in first or second year. So the problem is, with some of these, it's not so much that there is some confusion, there can be, but when you get involved with some pretty involved calculus, it can be pretty tough to be able to switch back and forth. So I would like to do it this way, and then of course you go back into first year and your professor's back doing this again. It's not so bad because you have these variables you've kind of learned already, but you can always go back to these because you know what they're talking about. So that's why we're going to do it in this course, like that. So if we take a potential function, it doesn't matter what it is, this is going to be typically 2 or 3D, whatever, mapping to a single variable. Okay, potential energy is not a vector, so it will always be a single number. And so when you do this, you would take that potential calculation and you would take its derivative of x, y, and z, and it generates a vector. So this is a mapping from R to R3. Now, be clear, this is not a space curve in the general sense of the context, okay? What we're looking at here is how a potential function is changing with respect to position. This has interesting implications. Now I'm going to retreat to single variable calculus to keep it a little bit reasonable. So we have a South Sea island that is a volcano. We'll just keep it simple. I have parabolic slopes to it here and a squared function here, okay? And what will happen is you take the potential energy is going to be mg times the height, okay? Not squared, just the height, whatever that is. It could be a function squared here of the radius. We could do that if we wanted to, perhaps, making the calculus a little more complicated. But let's just do it this way. So when we take the derivative, of course, the r cancels, and we simply get the force of gravity, the local force of gravity. And so there's an example from grade 11. You can see that dividing through or taking the derivative with respect to the position of something will give you the force, something you recognize. Now, of course, we can just do the mathematics here. We could say that our potential, arbitrary potential in some x, y, z universe might be, let's say, x, y cos y times e to the z. Okay, something arbitrary like this. And so if you put in an x, y, and z, you get whatever this is in different places. And so then the gradient of this is equal to then di v di x, comma di v di y, comma di v di z. And this would be then a vector function that would tell you what the force is with appropriate constants anywhere on this interesting surface here. That's a pretty amazing thing, okay? Well, let's just step through this because it's not too difficult. We're going to take the derivative with respect to x. The rest of this stuff is a constant. So we simply have y cos y e to the z, comma, and then we have di v di y, and it's exactly the same situation. Well, actually, no, we've got a problem here. We're going to have to try a little bit harder. So we're going to have x e to the z, and then we would have negative quantity, negative sine y, negative sine y, plus cos y. Okay? And then finally, these things here, so if we're taking the derivative with respect to z, these are constants, and the derivative of z is e to the z, so you simply have the same thing, x, y, cos y, e to the z. And so here now becomes a vector function, 3 coordinates, that will tell you what the force is if you know your location, okay? If you have this arbitrary potential function, which is way more complicated than gravity is, okay? And we call this the gradient, because in many ways you can model very nicely. And so this is one case where the mathematical term makes sense in our everyday experience. Now we can multiply this vector by a scalar, like we've done. We could now turn around and take del and do a dot product and decide what that tells us. So let's suppose we take di-f, and this is di-f(x), di-f(y), di-y, plus di-f(z), di-z. Okay? So let's suppose f of x, y, z is equal to xz, y cos z, xy, z. Let's just say that's our force that we're doing here. So then this is called the divergence. When Maxwell invented this concept, he did it the reverse. He called it the convergence. The vector field, all those little arrows around are coming together. He called that a convergence. And in more recent theory, of course, they flipped it and gone the other way. But that's semantics. So what we do here is, I've already calculated, oh sorry, I have my force, pardon me. So now we have the divergence. So del dot f in this example would be, so we take the derivative here with respect to x. So this is going to be, so I've already done, I guess yeah, I did it up here. Okay, fine, we don't need the parentheses. So we'll have z plus, and I didn't put any product rules in here to save you some time, di-fy, di-y, so that'll be cos z, plus, and then we have xyz, so that'll be just xy. And that becomes our divergence, okay? Now, let's imagine, from a practical standpoint, we have vector fields. Now, the things you already know about, let's start off with, say, a charge on a proton, or a positive charge. You're going to have the field lines radiating away in 3 dimensions. And what you're seeing with those arrows is they're spreading out, okay? And that will give you a divergence that's positive. It's spreading out. If the charge was negative, they'd be coming inward and the divergence would be negative. Let's take a little more involved case, and not getting into the numbers here because that's not necessary. If we take the example I gave a few minutes ago of the water coming out of the room, you have all those arrows as the water rushes up. But what do we know about the water as it's coming? It's going to come together to go out the door. Those velocity vectors are going to converge as the water rushes out the door. So we have a negative divergence of these vector functions as they approach the door. Okay? And that divergence will be a function of position. So when we come back to this here, you can see here that this is clearly x, y, and z are clearly positional units. And so that divergence will be a location-based calculation. And it's pretty obvious if you think about it, because the water could be coming close together, going around a corner, and the way the vectors are coming together will change depending on location. If we took the back corner of the room, which was as far away from the door as possible, the divergence would be basically 0, because all you're really getting there is the water going down initially, and maybe a trivial amount of movement. But the amount of converging and or diverging is trivial. Okay? Now again, this is just an introduction to make you aware of the types of things that we try to analyze tell us about these vector valued functions. And so this is just a little bit of foreshadowing. Now the last version, of course, as you can see by the pattern here, is that we could do a cross product, okay, where we take del and we cross it with f to get a cross product situation, which of course will produce a vector. So let's have a look and see what that would tell us in the most general sense. And we'll just keep the same vector function we had, so we don't have to reinvent the wheel here. And we remember from the matrix lectures how we compute the cross product. So, and we call this the curl, and we'll come back to why it's called that. So we have del cross f, and we call this the curl of f. It is also position dependent. So let's see what we have. So once again, we'll just use the definition of the cross product, which is stolen from the determinant definition to do this calculation. So this would be equal to, and we just have to follow this through in the most pedantic way. So di dot x die y, die z, and then the x coordinate of f, the y coordinate of f, and the z coordinate of f. Remember, these are functions, not just numbers. Okay? Why can't I do this correctly? My goodness, Henry, you're such a... All right, let's try it again. Let's make it a bit bigger. So we have I hat, j hat, and k hat. And here we have die x, die y, and die z. And finally we have the x, y, and z coordinates of the force function. And that is these functions here. Okay? And so then we just follow this through in the old-fashioned way here. So we'll have curl F is equal to, so now it's going to be I hat times the determinant of die y, sz, die z, and fy. Okay, minus, we always have to remember that. And then we have die x, die z, and fx and fz. And this is j hat. And finally, plus, and now we have die x, fx, and die y, and fy. And this will be k hat. Now that's the pattern. Let's evaluate all of this based on the variable and the function that I've given you here. And let's see what we get. So in this first determinant, you're going to have, so once again we'll have curl F at x, y, z. And then we're going to have, this first determinant is going to be die f z die x, die y, pardon me. Okay, and then this will, and then this is minus based on the determinant rules for a two-dimensional matrix. Then we're going to have die f y die z. Okay, parenthesis, calculate that times I hat minus, and then we have, so this will be die, it's going to be such a big, I guess we die f z die x minus die fx dot z, j hat, and finally plus, and we'll have die fy die x minus die fx dot y, k hat. So, and then we will now actually do the work here. So let's just do a little bit of pencil work here. So die f z die y. Go over here now. So this is f z die y, that'll be x z. And then we have die fy die z. And here we have the y is just a constant. The derivative of cos is negative sign. So we're going to have negative y sine z. Now what else do we have here? Die f z die x. And that would be yz, of course, very similar pattern. Die fx die z. And here we have the z, so simply just x. And then the last two, we're going to have die fy die x. And notice here that there's no x here, so the derivative is 0. exact same thing is true here. There is no y here, so we'll also have a 0 here. So when we're all done, we're going to have x, z, plus y sine. So it's plus because this is negative and this is also supposed to be minus. Quantity times I hat. And then minus, then we have yz minus x, j hat, and then 0 k hat. So, because 0 and 0. So now, if we took it as a coordinate system, we would have curl f is equal to quantity. Then we're going to have xz plus y sine z, comma, yz, and this would be, so we could actually do this another way. Multiply through by -1, we're going to have x minus yz and 0. So the amount of, so what does this mean? Okay, we can do this calculation, it's all very nice, but what does it mean? Well, one way to look at it is simply, this is the amount of rotation that the vector field is doing about the 3 cardinal axes. And so what we're basically saying in this final computation here is that there's no rotation around the z-axis. We have rotation around the x and the y. Now, how does this manifest itself in the real world? And the best way I would suggest is, let's start off by thinking of water flowing through a pipe. So if we had 2 veins, like so, in the pipe, water's coming towards me, 2 veins like this, very thin. If the water's flowing in a very linear or laminar way, okay, then those veins will not rotate because there's no forces or velocities pushing to the sides of the flow. Okay, flow is not turbulent, if you feel, rolling around that central axis. Okay, if we extend this to 3D and we see smoke billowing out of a stack, okay, what you're getting there is rotation. And that's what causes this billowing effect, or what you might want to call turbulence. If you see an explosion and you have a central cloud, kind of a mushroom effect, you don't have to have a nuclear detonation for that, it's just a bigger version of it, but smaller explosions will do it too, because the thermal currents in the center where the heat source is are very aggressive. And as they cool, they get pushed to the side by the updraft. And so you're going to get tumbling. And there's rotation in those cases as well. So it's very cool that you can use these ideas to model. So the biggest challenge with any of this is what does the function look like? Now, at this elementary stage, we're not going to be calculating horribly difficult functions that you may get later on if you do research in this area, be it in fluid mechanics or aerodynamics or something like that. But that's not the problem. Right now, we just want to be aware that these things exist, and that how you can actually do some of these calculations is pretty amazing. So that is the end of this vector operator lecture. And again, I thank you for watching. If you find these lectures useful, please consider subscribing and tell a friend. Thank you very much.